Hello, this is Mr. Craig, and I want to discuss bond energies, the third law of thermodynamics, and introduce Gibbs free energy today. This is day 110 for thermodynamics. Let's start off with talking about bond energy. Bond energy is the amount of energy that's required to make or break a bond. Breaking bonds in an endothermic process requires energy to be incorporated into the system. The bond energy is always a positive value. You'll be given a sheet on actually examples part 2 where you'll have a list of bond energies. The really bizarre thing about bond energies, number one, it does not appear on the equation sheet. Number two, when we talk about delta H, all the equations that are on the equation sheet when it deals with delta H, delta S, delta G, it's the sum of the heat or the sum of the products minus the sum of the reactants. However, with bond energy is opposite. It's actually reactants minus products when we actually add up all the bond energies. Hopefully that'll make a little more sense once we do an example in the next video. So here's another point. When a bond is formed, energy equal to the bond energy is released. Bond energies will always be given to you. So you just need to know how to use them. So again, take the sum of the bonds that are broken in the reactant end, and then subtract that from the amount of energy of the bonds that are being formed from the product end. All right, third law of thermodynamics. We started talking about entropy a little bit the last time we spoke, and again, entropy deals with chaos, disorder, randomness, and some people may argue and say, well, it's not really chaos, but when I think about disorder, I think a lot about chaos, how the order of a system changes, becomes more disorganized, and the universe really favors that. So again, when we talk about delta S and doing some delta S calculations, the only time that you'll have a value for any compound or element that we're working with entropy that has a value of 0 is at absolute 0. And that absolute 0 means that those particles are not moving because they have no energy. Now, what's the reality of us ever working with anything at absolute 0? None. So with delta S, you'll always be given some values. Now when we look at delta H and delta G, you'll notice that if you're looking at anything in its elemental condition at room temperature at 25 degrees in 1 atmosphere, say like oxygen gas, that will have a delta G and a delta H value of 0. So we don't have to do anything to get those elements into those conditions because nature has already done that for us. So we don't have to make any bonds, break any bonds, do anything really crazy with that. So when we talk about the delta H and delta G values for that, other than talking about bond energies, and that's a little bit different. But if we're looking at oxygen gas or anything, even a metal, say like iron metal, those should have values of 0. So sorry about beating that up a little bit. At the molecular level, entropy is often described in terms of motion of particles within a system. So again, the more motion that these particles have, the higher the entropy, the higher the disorder. The motion can involve the entire particle moving about, vibrating of atoms within a molecule. That typically takes place within solids, or the rotational movement within the entire molecules of the atoms within a molecule. So don't worry about that. Just realize that if we have a substance that's not at absolute 0, there will be an S value assigned. And you'll just need to know how to use that. Okay. Increases in motion are associated with higher entropy values. Just as I stated earlier, we would expect things that are moving more quickly, more often, should have a higher disorder value or a higher entropy. There are a few general trends about entropy that you should become familiar with. The AP exam will occasionally ask you to pick from a list the substances or reactions that have the highest entropy. And you'll see this on the test. I promise you'll see it on the test. I promise you'll see it on the AP exam within the multiple choice section. So some things that we need to realize, and I'll discuss more of these as we start doing some delta G calculations more often. Number one, when a solid melts and it goes from a solid to a liquid or sublimates straight into a gas, we are increasing the entropy because there's more motion that's possible. B, when a solid dissolves in a solution, so when we take, say, solid sodium chloride and we place it in water, it will break down into its ions. It's becoming more disordered. When a solid or liquid becomes a gas, obviously more motion. When a gaseous chemical reaction produces more molecules, so again, say if we start off with 3 particles on the left and then we end up with, say, 5 on the right, on the product side, we have increased the entropy. We have increased the amount of disorder. So more particles can and should be associated with an increase in entropy. When the temperature of a substance increases, you better believe it, as we increase the temperature, so do we increase the motion of those particles. So these are all examples of increase in entropy. So if you want to take the reverse of all those, that's a decrease. Calculating entropy changes, again, it's this equation here where we look at delta S is equal to the sum of the delta S products minus the sum of the delta S reactants. And again, those values will be given to you, and you'll see some examples of those on the second example sheet. All right, Gibbs free energy. I briefly want to talk about Gibbs free energy because we're going to talk a lot more about it. We will not use this equation today. Actually, we won't use this equation today. We won't ever use that equation. But this equation will have a lot of application a little bit later on. We'll be able to determine a little bit later on, I can't remember if it's the next lecture or 2 lectures from now, delta G deals with whether a reaction is spontaneous or not. Now, we do know that when we look at delta H, that deals with the energy of the reaction. T is the temperature. No big deal there. It's actually at a temperature. And delta S deals with spontaneity. So whether a reaction takes place or not doesn't mean, I'm sorry, not spontaneity. I take that back. It does not mean spontaneity. It actually means entropy. So it's order and disorder. So delta G again is the spontaneity, delta H is the heat, delta S is the chaos, disorder, and randomness. So when we do delta G calculations a little bit later on, not today unfortunately, if the delta G is negative or it's less than 0, that means that the reaction is favored in the forward direction. In other words, it's spontaneous when the reactants react together and form products, just like all the reactions that we're accustomed to. If delta G is equal to 0, that means that the system is at equilibrium. Now again, it's not spontaneous in the forward or the reverse direction because we spoke about spontaneity earlier on. It's just reacting in both directions. Don't ever think that a system at equilibrium is spontaneous in both directions. It's spontaneous in neither direction. It's just reacting to form products, and the products switch over and form reactants. That is not a spontaneous act. When we look at delta G is positive or greater than 0, then the forward reaction is not favored, but the reverse reaction is. So if we force the reaction to make some products, those products are immediately going to switch back into reactants. So we'd have to put a lot of work and a lot of effort into making products. But I don't know why we would, because the system itself will automatically shift it back and form the reactants again. So we'll do some calculations with that. We'll do some delta G calculations that look like this today, where we take the values that are given for delta G, the products minus the reactants. But this equation has a little more oomph a little bit later on, but we're not going to talk about that just today. I highly recommend that you look at the next video. So take a look at examples part 2 from day 110. And as always, I hope this has helped.